And with that, I'm going to move on straight to my talk. I embedded a programming language in debug information, and I'm going to tell you all about it. OK, so if you have any questions while I'm talking, please drop them in chat. I will keep one eye on it for the whole time. I cover some pretty weird stuff, so if you want anything clarified, just let me know, and I'll get to it. An alternative title for this talk is DWARF Shenanigans. The agenda for today. I'm going to give you an intro to the DWARF debug information format, which is where I embedded an interpreter. I'm going to tell you how I embedded custom programs more generally in DWARF. I'm going to give you an intro to the BF programming language, which is the language I embedded, and then how I implemented a BF interpreter inside DWARF. First off, why? Why did I do this? Why am I telling you? Well, I was writing a DWARF parser, and I was thinking, hey, this thing looks suspiciously Turing-complete. I wonder if I can write a programming language in it. And it turns out you can if you throw enough time and gray hairs at it. But I wanted to learn about executable and debug information formats, or learn more about them. And this is kind of what I hope you'll get out of the talk, a bit of knowledge about how this stuff works under the covers. Also, it was just a challenge to implement a language in such a constrained environment, and I had to come up with and use a lot of neat tricks in order to do so. But mostly, it was fun, and I hope you have fun learning about it. OK, an intro to DWARF. Not like this. So DWARF information is a binary encoded format for linking machine code back to the source code that produced it. And it does this in a number of different ways. It has a line table, which links the source lines to machine instructions. Like if you want to set a breakpoint on line 9 of cat.cpp, then you need to know to which machine instruction that corresponds in the running program. Similarly, if you want to set a breakpoint on the pet cat function, then you need to know where the code for that lives. Most importantly for us is locating variables at runtime, because the way that variable locations are encoded in DWARF is with DWARF expressions, not like this. So DWARF expressions tell us where a variable lives. They can also restore registers in stack unwinding information, but primarily interested in this form for now. And this can be in a number of different places, right? It could be in a register, could be at some address in memory, but it could also be a bit more cluster and then dereferencing the address that's there and then adding some offset to the result, for example. And it could be even more complicated. It could be stored, different parts of the data can be stored in different locations. So DWARF expressions can be quite complex, and they support expressing these complex locations. So DWARF expressions are a binary encoded sequence of instructions that run on a stack. Dust Candy says, are there dwarves in Microsoft formats, or is this just in ELF? Yeah, I'm talking about Linux systems today, and I will be getting to ELF later. So let's look at an example of a DWARF expression. Say we want to do exactly what I just said, read the R12 register, dereference the address there, and then add some offset to the result. I can issue the DWOP breg12 with 0 as an offset. And on the right-hand side is kind of what the stack might look like. Here's a value which might be in that register. Then I can dereference that by issuing the DWOP deref instruction, and that will read that address and push the value which is there back to the top of the stack. Now I want to add an offset, so I can push that offset onto the stack. So now we have 2 values on the stack. And then I can use DWOP add to pop the top 2 values, add them together, and push the result. So you can see kind of how we build up a program with these operations, and they're fairly generic. And you might be able to see how we can start thinking about how we can use this stack to implement our programming language. But that's getting ahead of ourselves. Importantly, we also have control flow, quite limited control flow, but control flow nonetheless. We can branch, which is a conditional branch, and skip, which is an unconditional branch. And these basically move the program counter forward or backward by a given offset. Reasonably straightforward. Okay, so how did I embed the interpreter? Now, there's a problem. DWARF expressions are encoded in binary, and I don't want to handwrite that. That would be a nightmare. And this was already a nightmare enough as it was. So I wrote an assembler which takes textual representation of a dwarf expression and converts it into a binary representation of that same dwarf expression. And it's mostly fairly simple. The kind of core of the assembler is just a massive if-else statement which handles all the opcodes. So if the opcode is DWOP adder, I get rid of the prefix just so I don't have to write that everywhere. Then I just output the DWOP adder opcode into some byte stream. I then parse the address operand as a 64-bit integer and output that into the byte stream. Fairly straightforward. There could also be simpler ones like DWOP deref, which you saw on the previous slide, and that doesn't take any operands, so I just output the opcode. Or some will take operands which have to be encoded with a different sized integer, for example, like deref size. Just like DWOP adder, it takes an integral argument, but in this case, it has to be encoded as an unsigned 8-bit integer. So I have to make sure I pass the right size. And this kind of follows for the rest of the opcodes. There's only a few dozen, so it's not too bad. Slightly more interesting is I want to support things like this, having labels and comments so that I can kind of make my own functions and say, hey, this is kind of what the input to this function should be. This is what the stack should look like when this function is called. And then, down at the bottom there, I've got a skip instruction. And instead of giving that an offset, I want to give it a label and have the assembler work out what the byte offsets are. Because if I write that myself, every time I change my code, I'm just going to have to modify these, and it's going to be a nightmare. Okay, so how do I do that? I basically loop over all of the instructions in the dwarf expression. If it starts with a dot and ends with a colon, then that's a label. So I just make a note of the label's name and where its position is in the byte stream. If the line is not empty and it doesn't start with a hash because I use those for comments, then I encode the instruction. And that uses just that massive if-else statement that you saw earlier. Something to draw your attention to is this final argument fix-ups. This is how I handle references to labels, because you might jump to a label which is only defined further down the program, so it hasn't been read yet. We don't know where it's going to live in the byte stream. So I just keep track of all of those. And then right at the end, after I've dealt with all of the instructions, I loop through all of these fix-ups. I get the byte offset into my byte vector at which the label exists. I work out the difference between where the label is and where the reference is, encode that as a 16-bit integer because that's what the standard expects, and just copy that over. I write some zeros into the byte stream in the first place and then copy the real data over here. So that kind of works. We can now generate binary dwarf expressions, but where we put them? The answer is ELF files. So let's talk about ELF, not like this. So ELF files are how binaries are encoded on Linux. They have a header, which describes high-level information, such as, oh, I am an ELF file, and I am an executable, and I am for 64-bit systems, all that kind of stuff. And it has sections, which describe areas relevant to linking together multiple object files and libraries, and then segments, which describe areas relevant to program loading, such as, hey, operating system, please put this code and this data in this position in virtual memory when you load my program. We have a question on endianness, I am just dealing with 64-bit Linux, sorry, x64 on Linux. So I just say everything is little endian, and I don't care about other platforms because it's difficult enough doing it for a single platform. There's also how small can you make an ELF file? I can't remember exactly, but they can be very, very small. Like you don't even need section headers. You can strip those out. It can be pretty minimal. But we will see a bit of this later. So that's how it goes. These are the most important sections that I need for my needs. I have the .debug lock section, which is where DWARF expressions live, or well, where some DWARF expressions can live, but it's the easiest place to put really big DWARF expressions, and I need really big DWARF expressions. Then there's the .debug info section, which is where the majority of DWARF information usually lives. And in there, I put an entry for a DWARF program variable, and that is how I link together my interpreter program and the program which I'm interpreting. That program I store in .strtab, which is just the string table. So this is going to get loaded into my into the address space when the regular x64 program is loaded by the operating system. Okay, so I'm going to show you a bunch of code of kind of what I did when I built my ELF file. I decided to do it completely by hand because taking an existing ELF file and modifying it is a massive pain because there's a lot of cross-references between everything. And as soon as you like insert bytes into there, then you mess up everything. It's not fun. So I just wrote an entire ELF file by hand. So I'm going to show you a bunch of the code. I don't expect you to read through all of it and understand everything I'm doing. This is just to give you a kind of feel for the nonsense and shenanigans that I got to. So first off, I had to define an ELF header. Up the top there is the magic number, which says, hey, I'm an ELF file. There's the file type, which is executable. I say that it's for x86-64, and then a bunch of other metadata about the ELF file. One other thing to note here is that OXFFFF that I put for the section table file offset. The section header table lives at the bottom of the ELF file. So I don't know where it's going to be yet because I don't know exactly how much data I'm going to be writing into this ELF file. So I just leave it as OXFFF and I fill it in later. I have to make section headers for all of the sections. I only have maybe like 8 or 9 sections. So here's one for the .debug lock section. It has type program bits. I don't know what the file size is going to be yet, so I leave that as OXFFFF. I have to have some x64 code so that can get loaded, and so that my if I run this through GDB, that GDB can stop on some valid instructions. So this is essentially a like return 0 in x64 assembly, x64 machine code, which I just encode as a byte array. And then I need my program headers, which describe segments. So I have a single program header, which tells the loader to load both that x64 code you just saw and the string table, which holds the BF program that I'm going to be interpreting. Then I also have to write the DWARF information by hand, which is kind of a nightmare, and it's huge. So I'm only showing you a tiny bit. This bit is where I am describing the layout of the DWARF program variable entry. I'm saying it has a name and it has a location, and that location, that's where I'm going to stick the my interpreter. Then once I've done all of that, defined all my data, I have to write it out to a file. So I basically keep track of a big byte stream. I insert the ELF header into the byte stream. I insert the program headers because those come next. I insert the text section. After I've inserted the text section, I know where it's going to live. So I update the text section header, which I will write into the byte stream later on, and go on doing that with all of the data I need for my ELF file. And after all that's done, I finally write this out to just a regular file on the file system. I just open a file in binary mode, blit it out, and we're done. With all of that, I can run my, I call DW assemble, which will assemble some dwarf expression into a binary that contains the dwarf expression. And if I run the file program on it, which is just a regular Linux thing, which tells you about the file, then it says, hey, this is a 64-bit ELF file for x86-64. So Linux is reasonably happy that we've written a valid ELF file, or something that looks valid-ish. We can even use tools like readelf and dwarf dump for understanding more about the file. So I'll show you a few bits and pieces. This is readelf minus capital S, which gives you the section headers. You can note that you can see the most important ones. Here, the .stir tab, which holds the BF program, the .debug lock, which holds my interpreter, and the .debug info, which links them together. What happens if you run it through strip? I think it would stop working because I rely on some stuff that strip would strip out. But I haven't tried it. This is dwarf dump, which gives you a dump of the dwarf information. So you can see this is the .debug info section, and it contains a dwarbf program variable, and the location of that points at the .debug lock section, and the top instruction there is the address of the BF program in the string table, or at least where it will be in virtual memory when this thing is loaded. And then that ... is the rest of my interpreter, which I'll show you in a bit. And then the final thing is I can look at the string table, and you'll note this mess of symbols. This is my BF program. Might not look like a program, but this is a program, and now I'm going to tell you all about this language. So, intro to BF. This is what you just saw laid out on a single line. I'm not going to walk through it. This is a program to calculate the 6th Fibonacci number, which is 8. And this is the entire program. We'll tell you about the language. It runs on a theoretically infinite tape of cells. Every cell is a single byte, goes from 0 to 255. And there's a pointer, which points at one cell at a given time. So there's 8 instructions in BF. There is left, which moves the pointer to the left. There is right, which moves the pointer to the right. There's plus, which increments the value currently being pointed at. There is minus, which decrements the value currently pointed at. Then there's IO instructions. There's comma for reading one character from standard in, closed in square brackets, and anything between these square brackets will be repeatedly executed until the value which is pointed at by the pointer is 0. And that's pretty much the entire language. All right, writing the interpreter. Cameron says, I still believe that BF is the best language for anyone to start with if you're looking to write your first interpreter/compiler. I agree. I have a talk which I gave at CPPP where I wrote an entire x64 BF compiler from scratch on stage. And it's such a fun language. Yes, we're doing a BF interpreter. BF is best friend language. Yes, thank you, Josh. All right, writing the interpreter. So I'm not going to show you much of the code for the interpreter, because it's really gnarly and horrible. I'm going to show you some of the algorithms that I used in implementing it. Now, the top left here is that infinite BF tape. The bottom left is the BF program with a null terminator at the end, just to show when it's finished. And the right-hand side is the contents of the DWARF Expressions stack. All right. So I want to interpret the first instruction of my BF program, which is write, which should move the pointer to the right. I hold on the stack 2 values right now. The top value is the index of the cell I'm currently pointing at, which is 0. And the bottom value is the current BF instruction character that I'm pointing at. So if I want to move the BF pointer to the right, I just increment the top value on the stack by 1. And then I have to move to the next instruction. So I flip the 2 elements on the top of the stack, add 1 to here, and flip it back. And now I'm ready for the next instruction, which is the left instruction, which I just decrement the value on top of the stack. And then flip again, increment the character pointer, and we're pointing at null, so we're done. We just interpreted a BF program. Now, left and right are several orders of magnitude simpler than the rest of the instructions. So that's why I walked through them first. But after I did this, I came across several difficulties. I mean, I am like implementing a programming language in a language designed for simple address computation, so it was never going to be a walk in the park. But some of the main problems are there's no way to do I/O, which is bad. There's no function calls. Kind of. There are some function call expression instructions in DWARF expressions, but they're not very well supported. One of them is not even implementable as it's specified, so I don't use those. There's no way to modify any stack elements beyond the first 3. Now that's a big problem because we have an infinite tape, which we need to be able to modify. So that's not great. I can copy any of the first 256 elements to the top of the stack, which is good, but only with a compile time constant index. All right. I did manage to overcome most of these. I did like quit this project like 3 different times thinking it was not possible, but most of them I overcame. The having no way to do I/O, that one you just can't get around. I can't read from standard in and write to standard out. There's just no way to do it. So I don't implement those instructions. Someone finds a way to do it, let me know. Only being able to modify the top 3 elements. This one took me a long time, so I can't just have an infinite tape or like treat each value on the stack as the value of a cell because I can only modify 3. So what I did was something like this. So again, top left is the BF infinite tape, bottom left is the BF program, right-hand side is the DWARF expression stack. I've already interpreted the first 2 instructions, so we're pointing at this BF cell at index 2. Now you'll notice here I've introduced a new value onto the stack at the bottom there. It's just a bunch of Fs and then a byte of zeros. So what I do is I maintain a list of tagged memory update records. And that list is terminated by this special bunch of Fs, 2 zeros. This is like an end of list marker or a sentinel, whatever. So if I want to interpret the plus instruction, which should add 1 to the currently pointed at cell, what I do is I read my memory record update list. The first value there, currently, if there's only 1 value, it's the end of list marker, so I know that I do not have a current memory record for the cell at index 2. So I create one. There's some bitwise operations that I can do with DWARF expressions, so I use those to create kind of a tagged value. So most of the integer is dedicated to the cell index, which is 2, and then the final byte, because these cells only use a single byte, that stores the value of the cell. So the top of the stack currently says the value of cell at index 2 is 1. And then I rotate that into place because I can, remember, manipulate the top 3 elements of the stack. And this is how I represent my BF memory. So then I interpret the right instruction, which moves the pointer over. And now I have another plus instruction to interpret. I do the same thing. I start reading the list. Here we do have a valid record, but it doesn't match the the cell we're currently pointing at. 2 is not equal to 3. So we look at the next one, which is, again, the end of list marker. So we create a new update record and rotate it into place. So now you can kind of see how this builds up. We move the pointer left to do the left instruction. And now things go a little bit differently. For our final plus instruction, we, again, start reading list. We got a record for cell 3, which doesn't match. This time, we got a record which matches the cell we're currently pointing at. So we do a bunch of bitwise operations to update the record and rotate it into place. Note, I cannot modify the old record. I have to push a new one because I can't modify anything past the top 3 values. So I create a new record for every single variable modification. So I can only support like 250 odd variable modifications, which is not a lot, but hey, it's what I'm working with. So I was pretty pleased with that. It works pretty well. Having compile time indices only for indexing the stack. That's kind of bad because I need to be able to walk down that memory update list to find the relevant entries. So this is done with the DWARF pick instruction, which takes some compile time index, which is a single byte. But I want to do this at runtime. So I wrote basically a massive switch statement in a dwarf expression. I called this pick table, and this takes one argument, which means that it has the runtime index you push to the top of the stack before you jump to pick table. And I just do a bunch of checks. I check, I only start at number 3, because that's the first stack value that I want to be able to copy up to the top. So I check the argument against 3. If it is 3, I call pick 3. Otherwise, I check against 4. And if it's 4, I call pick 4. And so on, so on, so on, so on, up to 255. It's horrible. I wrote a Python script to generate this code for me, but it works. So yeah, you can translate runtime indices to compile time indices. Another problem, no function calls. For this, I basically emulate return addresses. The problem here is that I need that pick table implementation like 6 different places in the code, and I don't want to have 6 different versions of the pick table because that starts to become intractable. You can only jump, you only have 2 bytes for jump offsets, and that starts to become a problem when you have these pick tables, which are too large. So I basically implement return addresses. So in the implementation of plus, when that needs to call the pick table, it first pushes 0 to the top of the stack. And then right after it calls the pick table, it has this pick table plus ret label. The implementation of minus pushes 1 instead, and then has a pick table minus ret afterwards. And I do similar things for the other 4 places I need the pick table, pushing 0, 1, 2, 3, 4, or 5. So that gives kind of identifier for where to jump back to after the pick table is finished. So at the end of the implementation of pick table, I just do a switch statement again, basically. Check against 0. If it is 0, I jump back to plus ret. Otherwise, I check against 1. If it was 1, I jump back to minus ret, all the way to the rest of them. So apart from the I/O, that's our problem solved, more or less. And with that, I can get my BF program, which generates the 6th Fibonacci number. I can run DWARF on it to embed interpreter and this program into an executable. I can run GDB. This is plain GDB. I did not modify it in any way. I can run plain GDB on this program. Can run start I, which just starts and immediately halts the program. And I can say, hey, what's the address of the DWARF program variable? And because my interpreter is stored in the location information for that variable, then when GDB sees this, it's like, oh, hey, yeah, I'll run this DWARF expression, which happens to be a programming language interpreter, and gives me back the result 8, which is the correct answer. So this game, it's about 2,800 instructions of DWARF expression. It gave me several gray hairs. Like I said, I gave up several times before I got this to work. It does need about 80,000 instructions to be executed to calculate the Fibonacci number. So it's not the most efficient programming language, but it kind of works. It's pretty cool. So thanks very much for listening. And if you do want to check out the code, then you can find it here at github.com/tartanllama/dwarfbf. And yeah, if you have any questions, feel free to drop them in chat. I will be around.